Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in this course Advanced Thermodynamics and Combustions, and in the first module, that is review of basic thermodynamics, we have 3 lectures. The first lecture we covered on temperature and zeroth law of thermodynamics. Today we will be discussing on the first law of thermodynamics, and which is mainly dealt with work and heat transfer. And in this lecture number 2, which is work and heat transfer, that is first law of thermodynamics, we are going to discuss the following topics. The first one is the basic concepts of work and heat. Then we will move to the thermodynamic definition of quasi-static process and subsequent work transfer. Then we will move on to generalized equations for work system, and subsequently how that work equations can be applied for a composite systems involving multiple number of systems and processes which are non-thermodynamic in nature. Then we will after discussing the concept of work and heat, we will give the definition of the first law of thermodynamics, and with this first law of thermodynamics it gives another concept which is heat transfer or heat, which is and it is the another form of energy. Subsequently to this discussion on the first law of thermodynamics, we will define some parameters, and that which is heat capacity and its measurement, and the last segment of this topic is the modes of heat transfer. Now, let us move on. First, we will give the thermodynamic definition of work and heat. We all know that the energy interactions in a thermodynamic systems can occur in 2 modes, work and heat, and there are some basic definitions which needs to be followed if you want to talk about work. In mechanics principle, work is nothing but force times displacement, and later on we convert the work to energy. Subsequently, it can be kinetic energy, potential energy. So, sticking to that definitions, the thermodynamic sense of defining the work refers to the fact that whenever we define this work, it and side by side we can visualize that systems either rising or falling a mass systems. So, in the process of rise and fall of this certain mass, the potential energy of the system is changed, and that gets transferred in the form of work. So, in this work transfer mode, in one sense we say there is a paddle wheel arrangements which is used to change the thermodynamic state of the systems, and in this case it may be a liquid inside a container, and that thermodynamic state is going to change through this paddle wheel arrangement, and when you do some work on this paddle wheel, and that is possible through rise and fall of these mass systems. Similar work can also be introduced into the systems through an electric circuit, in which we can we can dump the work into the same amount of work through an electrical system, but still that also can be used, that energy can be used or can be viewed as rise and fall of a mass systems. Now, in this process of the change of energy interactions, we really do not encounter the change in the temperature, substantial change in the temperature. If this is not the case, and whenever there is a energy interactions by virtue of temperatures, then that systems we refer as a heat transfer mode. So, in same systems we can say that in a closed environment, a certain mass of liquid is getting heated by a burner. There is another viewpoint is that we can have a electric systems in a enclosed container, in which the water can be placed. So, this particular sense, there is no physical movement of mass systems. I mean, these systems cannot be viewed as a rise and fall of mass systems, rather it can be viewed as rise in the temperatures. So, in this category we say there is a temperature change, delta T is involved. In this case also delta T is involved, but so that is what they call it, they fall under the heat transfer, heat as the mode of energy interactions. But in this case we have the work transfer can be viewed as mg delta z. In this case also mg delta z. So, delta z is nothing but the elevations, which can be quantified in the form of rise and fall of weight. So, this weight can be, when it goes up, it does work on the systems, when it comes, that means work is done by the system. Having said this definition of work, then we are going to discuss about two form of this work. One is external work, other is internal work. So, in the internal work systems, that means this is mainly applicable for a microscopic system, where there is interaction of atoms, molecules, electrons, and in that case if the analysis of work when it is done, so that work is done by one part of the system to another part, then it is a internal work. But if a system as a whole exerts a force on the surroundings and the displacement takes place, then the work is said to be done either by the system or on the systems, and it is termed as external work. So, that means unless and otherwise specified, our viewpoint of work is always external work, and our viewpoint of heat is the part of energy transfer between the system and surroundings by virtue of temperature difference. Now, with this basic definition, we will now move to individual mode of analysis, that is work transfer. The thermodynamic definition of work transfer always refers to the fact that when there is a change of state from one to other, then the process can be specified as a quasi-static process. So, in a quasi-static process what happens? That means change of state of the system happens without any disturbance to the surroundings. So, in to have such quasi-static process possible, what we need to have requirement is a thermodynamic equilibrium between the system and the surroundings. So, this is possible only when the system exists in mechanical equilibrium, that means there is no unbalanced force. The system is in the thermal equilibrium with respect to surrounding, there is no transfer of energy by virtue of temperature difference, and in fact there is also no chemical reactions. So, by virtue of which it becomes the system is in equilibrium chemically with respect to surroundings. If these three conditions are satisfied, then and the change of state happens, then we say it is a quasi-static process. So, all the viewpoint of analysis of work transfer can be possible through quasi-static process. Now, again for heat transfer situations, we can recall our previous analysis that transfer of heat is possible only when the system the multiple systems they are separated by diathermic wall. So, diathermic wall means the information of between the systems can be propagated through heat transfer, but if you put an adiabatic wall, there is no question of transfer of heat or energy in the form of heat. So, these are the viewpoints in which we are going to discuss the more details on the work transfers. Now, when I say quasi-static process, the first basic definition we say that the work is nothing but force times displacements. Now, here the force can be interpreted in the form of pressure, displacement can be interpreted in the form of volume. So, that means whenever that means there is a change in the volume and there is a change in the pressure. So, we can define this in the coordinates PV diagrams. So, that is what we say quasi-static processes are often referred in the pressure volume diagrams. So, in a simple systems like we have a piston cylinder device. So, this piston is moving back and forth within these cylinders. So, in the process of moving we can view these systems that when the gas which is inside this container or this inside the cylinder, it gets compressed when the piston moves in the forward directions, and the gas expands when the piston moves in the backward directions. And we say that if there is the process occurs in very slowly, so that the displacement can be represented in the form of dx, small displacement for a given force F, then we can view this entire change in the pressure and volume of the gas, in which we can write that which gas which is at initial state I, its coordinates are specified as Pi and Vi, and when this is at final state, is final volume is Vf and final pressure is Pf, and initial pressure is Pi and initial volume is Vi. So, the work transfer in this process we can see there is an increase in the volume, and here the this is a, so you can say it is an expansion process. And in another viewpoint is that from the final system to initial system the process can also occur. So, so these two, first and second, they are referred to processes. Now, when I club them together, that means a gas goes from the initial state to final state in one path, and again it returns to the initial state in another path. So, these things we can say, if this case this happens, we say it is a cyclic process. And very specifically we can say that these processes can be defined, and when the in such a way that when the pressure remains constant, so it is isobaric process, when volume remains constant, it is a isochoric process. Then we also know that what is an expansion process, that means in the expansion process the work is generally done by the systems, and in the compression process the work is done on the systems. Another point I would like to emphasize the fact that the pressure volume diagrams which normally represents the work transfer is also called as an indicator diagram. So, in the same philosophy we can find out what is the work transfer that happens. So, starting from the first basic definition, when a force is exerted, displacement x dx, the work transfer, since if you can see this is an inexact differential because it depends on the path. So, dw can be written as p a dx, a dx is nothing but the volume change, and they can be integrated once you know this relation between pressure and volume. So, we can say work transfer, it can be integrated from P dV from when the volume changes from Vi to Vf, and in one case the work transfer will be negative, and in the other case, that means this is a situation for compression and this is the situation for expansion. In the process of work transfer, the volume increases. Now, moving further, this is another angle of representing this pressure volume diagrams, where the standard way of representing this pressure volume relations as P V to the power n is equal to constant. So, in the basic thermodynamics course, this is a very fundamental relations, and for different values of n we can say what are the nature of the processes. They can be isobaric. When you have say isobaric process, that means it is a constant pressure process. So, in this case n is equal to 0. So, here the pressure is constant, and when you say isochoric process, the volume remains constant, that means n is infinity. And if you say isothermal process, we say Pv to the Pv is equal to constant, that is nothing but Pv is equal to RT. So, n is equal to 1. When you say adiabatic process, n becomes gamma, and when you have polytropic process, so typically there is a standard number, we say it is n is equal, it is just a number n, it can be any value between 1 and gamma. So, this is how we define these thermodynamic processes in our analysis. So, for each case it is now possible to find out the work transfers. So, isobaric process, pressure is equal to constants. So, accordingly W12 can be calculated as P into V2 minus V1. For an isochoric process, so P d integral of P dV is 0. For an isothermal process, we say P v to the is equal to C, and since we have another relation P 1 V 1 is equal to C. So, this particular equation can be integrated. So, there are two forms. So, work transfer is equal to P 1 V 1 ln V 2 by V 1 or P 1 V 1 ln P 1 by P 2. Now, if it is an adiabatic process, P v to the power gamma is equal to constant, polytropic process P v to the power n is equal to constants. So, in that processes, the general definitions we can write as W12 as P 1 V 1 minus P 2 V 2 by n minus 1, and finally, this can be represented as P 1 V 1 by n minus 1 whole into 1 minus P 1 by P 2 to the power n minus 1 by n. So, this is for polytropic process. Now, when n goes to gamma, so this becomes adiabatic process. So, this is how we are going to calculate. Then moving further, we are going to have another definition, which is adiabatic work. Adiabatic work, the word adiabatic is normally used when there is no heat transfer, but work transfer when the system changes from state 1 to state 2, the work transfer is possible. So, in a situation when there is no heat transfer, how adiabatic work can be calculated. So, this particular things we can say that if you recall our PV diagram, so a system goes from initial state I to final state F. So, a typical or maybe one of the best processes, that is process 1. Through this process 1, it can go from one state to other, and there are multiple ways that state point 1, that initial state, we can reach to the final state by multiple ways. So, I can go in one line I can have another method by involving process 3. So, I can go from I to A, then A to B, then B to F, or I can have another process I to C, then I to D, then F. So, in this way you can say this different name of the processes we can have 1, 2, 3. So, there are 3 situations that I have mentioned here in which the initial state can be changed to the final state. Now, in this process of going from initial state to final state, what I am imposing a condition is that we can view this as if there is a gas that changes its states when the piston moves within the cylinders. So, through this we can go from I to F. But there are some situations, and in this process what I have mentioned is that this is a constant pressure process, but there are some situations that if without maintaining the constant pressures I can choose this path and reach the final state, and while moving in this route still I ensure there is no heat transfer. Now, while choosing another path 2, that is I, C, D and F, I also see that there is no heat transfer. That means, entire route is completely enclosed by an adiabatic wall for which there is no heat transfers. But ultimately, if we are able to see or do some experiments in which we can find out a parameters, and which is nothing but its internal energy, which is nothing but internal energy. What it says is that, and that this internal energy I am calculating at the initial stage as well as the final state, and what has been seen is that whatever path you choose, as long as that path is adiabatic, the internal energy change is equal to the adiabatic work. So, means that if I go from 1 to F in the process 1, which is adiabatic, I calculate what is UI, that is UF. So, for the process 1 we can say this adiabatic IF for process 1 becomes UF minus UI, and if I am also possible, if it is possible to also measure what is IF which is in the process 2, and I calculate this internal energy, I also have same value UF minus UI, and in the third process if you have this work transfer by adiabatic process, it becomes UF minus UI. So, what it means is that as long as the condition of adiabatic nature is ensured, this change in the internal energy is nothing but the adiabatic work done. So, this is the fundamental conclusion that we get out of this exercise. Now, when I say internal energy, then you put another definitions, what is this internal energy. So, quantitatively it is the difference between the functional values between the final state and initial state of the systems. So, the mathematical definition we can say it is a functional values between the final and initial state of the systems, and because of this reason instead of giving a value we call this as a internal energy function. Why we say function, I will come back to that point later, but the physical interpretation tells is that the increase in the internal energy function is equal to the adiabatic work, and this is the basic definition for conservation of energy. In fact, when this conservation of energy was in the beginning it was realized, it was started with a concept that finding adiabatic work and then equalizing it to internal energy function. So, moving very specifically we can say that in the viewpoint of graphical representations, we see that the internal energy is a state functions. Although we come to a different route, the work transfers in all the cases are equal, but when this work transfer, when you find this equal, try to equalize it with the energy transfer, this we say this internal energy du, it remains same for all the adiabatic path. And then it is stated that internal energy is a state function. Here I like to emphasize why we say it is a function. Since internal energy is a thermodynamic variable, the ideal way of representing them is in two independent variables. These two independent variables could be either pressure volume or temperature volume, because pressure volume they are internally related. So, the ideal way of telling this, that in the first expressions, if you say that u is a function of temperature and volume, then exact differential function du can be specified as dou u by dou t at constant volume into dt, dou u by dou v at constant temperature into dV. Now, if you say this internal energy function of temperature and pressure, then du will be equal to dou u by dou t at constant pressure into dt, dou u by dou p at constant temperature into dP. And because of this reason, we say that the internal energy has a functional relation. Then moving further, we are now able to discuss about internal energy, we are now able to discuss about work, and we have tried make a correlations, then we have a concept of generalized work. So, the generalized work, which is nothing but the thermodynamic definition of work, and for an hydrostatic systems, the pressure and volume representation is the most ideal way, and this pressure represents the generalized force in the intensive coordinates, where volume is the generalized displacement. And the third parameter, which is also important, is nothing but the another independent parameter, that is temperatures. So, a single equation exists, so that two coordinates are independent. We also know that a composite systems can be depicted by two hydrostatic systems separated by a diathermic wall that ensure both parts are same temperature. Other way is of looking at the system, this composite systems can be separated in a adiabatic wall. Through this diathermic wall, there is a information of propagation of energy in the form of heat. So, this particular thing shows that we are now we will now imagine a systems in which there are two gas system phase, and these two gas systems are separated by a diathermic wall, and in both sides there are pistons. The other part, and on the top of this we have a heat reservoir through which the information from this the part 1, that is gas in the system 1 and between the system 2 is possible through this heat mode. That means, if we can say this is a diathermic wall and this is an adiabatic wall, even though we put a heat reservoir, we cannot propagate the information between these two. And but this entire information, but if you do not imagine this to be an adiabatic wall, entire information can be routed through this diathermic wall. So, what through this process, now one sense we can imagine that as if we will put no restrictions on this top part in which this heat reservoir is kept. So, only information that can be passed from system 1 to system 2 is through this diathermic wall. initial conditions of this gas in the system 1 will be P V and initial conditions of the system 2 will be P dash and V dash. So, now it is a composite systems which involves the coordinates, that is pressure, volume and temperatures. And since we say that there is no restrictions of adiabatic in nature, entire systems can be in the thermal equilibrium. So, when I say there is a thermal equilibrium, that means there is temperature is constant there. So, in this there is a boundary in which there is a constant temperatures. So, entire 5 coordinates, although we have a multiple composite systems involving their 5 coordinates, out of this only 3 independent coordinates are possible, that is V, V dash and T. P, V are related, P dash, V dash are related. So, out of them we are only choosing one, and temperature is the another parameters. Now, if these 3 things can be plotted in independent axis systems, coordinate axis systems, that is temperature, volume V dash and volume V. And what we can realize, we can imagine it is a cube involving these coordinates, and for each plane we can assign some the thermodynamic definitions. For example, in this plane, in this particular plane we will have volume constant. In this top part of the plane, that is we have temperature constant, and in the third part of the things we have V dash is equal to constant. And as you say, there is no work across this boundary. So, that boundary can be imagined as a typical isothermal process and constant volume process. That means, when you say constant volume process, obviously there is no work. The straight line AB represents the process in which no work is done by the system. So, the AB system represents there is no work, because along this line there is volume remains constant. So, this is how we are going to realize a composite system analysis. Now, having said this composite systems, then again we will move back to the fact that we are looking at a situations when this work transfer is possible in a non-adiabatic processes. So, non-adiabatic processes involves heat transfer, because that is another part of mode of energy interaction, that is which is called as heat. So, it is a non-adiabatic process. One typical example can be given, that again we have same piston cylinder systems where heat is added and we relax the conditions of adiabatic. So, it is a non-adiabatic process, and if you try to quantify in this non-adiabatic process what is the change in the internal energy and what is the change in the work transfer. And in another situation, in a magnetic field also, when there is a strong magnetic field which is experienced by a liquid helium gas, we may see that there will be change of temperatures of this liquid helium. Some of the liquids may also evaporate. So, in some those situations where the adiabatic conditions cannot be ensured, then we say it is a non-adiabatic systems, and if you want to try to quantify the work transfer and internal energy transfer, we see that this adiabatic work is not equal to the change in the internal energy functions. So, this gives a definitions or concept which says that the difference in the energy follows the conservation of energy, which says that the difference temperature difference and allows the energy interaction between the system and surroundings in the form of heat. Then with this we will now move on to the definition of first law of thermodynamics. So, what it says is that for a closed systems for which the systems are at different temperature on which the diathermic work is done, then the energy transferred by the non-mechanical means is equal to the change in the internal energy and the diathermic work. So, this gives the formulation of first law, which signifies three aspects. First is existence of internal energy function, second one is conservation of energy, third one is heat as a energy in transit by virtue of temperature difference. So, based on that, if we recall this our understanding, the change in the internal energy functions is quantified as the difference between heat and work transfer. And here we must follow one particular sign convention, that this sign convention which says that heat is positive when it enters to the systems and it is negative when it is leaves the systems. Similarly, work is positive when it leaves the systems. In that sense, we say it is a work done by the system, and the work is negative when it enters the systems. In that sense, we say work is done on the system. Now, with these basic definitions, we are now going to talk about the definition of first law of thermodynamics for a very infinitesimally small processes, in which we can represent the internal energy function as an exact differential du, and the path functions are represented by dw and dq, which are inexact in nature. Now, if you want to equate them, we can say for an hydrostatic systems dq, that means when you say hydrostatic, it is just a pressure volume system, we say dq is equal to du plus pdv. Now, if it is a composite systems, that means there are non-PdV work. Non-PdV work involves work transfer by electrical circuit, work transfer through a magnetic field. So, this is an equivalent amount of PdV work, which it is represented as P dash dV dash. So, in a composite systems involving multiple method of work transfer can be represented, and for which the first law is written as dq is equal to du plus pdv plus p dash dv dash. Then the first law of thermodynamics gives the very basic definition of heat, and we will now try to quantify how we were going to evaluate this heat. So, for that we say we define a term called as heat capacity, and how we were going to measure it. So, heat is nothing but a calorie. So, prior to this development of work, when the heat people used to view as a heat, they call it as a calorie. They use the word calorie, how many calories of heat has been transferred. So, in a sense that this calorie is also used as the unit of heat. But subsequently, after the development of the first law, when it was realized heat and work, they are nothing but different names associated with energy, then the concept of heat definition got changed. So, we say that both has same unit, but the way or viewpoint is different. Now, whenever there is a change in the temperature difference, the energy exchange is will take place in the form of heat, and in a hydrostatic systems, if the diathermic boundary is such that the volume of the system does not change, then heat exchange is nothing but the change of internal energy. Now, in the process when the pressure of the system does not change, so in a case that either it is isobaric process or open systems, the change heat transfer change is or heat transfer is known as the change in the enthalpy. That means, enthalpy and internal energy, they are the very basic definition of the first law, which is applied for a closed systems and open systems. We also found out that within an adiabatic boundary, the heat lost or gained by the system A is also equal to the heat lost or it gained or lost by the system B, if the boundary, if the A and B are separated by a adiabatic boundary, which already we have proved. Then having said this, then we define this heat capacity for a non adiabatic process, we can represent as a internal energy capacity. So, heat capacity is generally referred to as internal energy capacity. So, when heat is absorbed by the system, the change in the temperature takes place depending on the states, and one way of quantifying them is representing this heat in the form of specific heat, that means change of heat per unit mass. So, and for a fluid systems, there is only one specific heat, which is defined as a average specific heat C, and this average specific heat by definition we say that when the systems goes from final state to initial state, we can say its average heat capacity with limit T f to T I d q by T that is equal to d q by d T. So, this is the definition of average heat capacity. Now, if this heat capacity can be represented in the specific forms, we say small c is equal to C by n, n stands for number of moles, which is related to the mass of the systems and molecular weight of the gas. So, this particular definition also holds good, only holds good for gas part. Okay. Then some very other basic definition is that the heat capacity can be negative, can be positive or infinite depending on the process that undergoes the heat transfer. Now, we are going to give some mathematical interpretation of this first law by including this heat transfer. So, we know what is the heat capacity now. We have the first law of thermodynamics, then let us correlate, and we also know the mathematical relations when a thermodynamic parameter is specified as the function of any other two independent parameters. So, with these three viewpoints, we have to now recall that what we understand is that how these properties or what I mean how these internal energy functions can be found out from the first law. So, you recall our thought that we have a specific heat at constant volume, that means when there is a change of heat with respect to temperature, when keeping volume is constant, we say specific heat at constant volume. When there is a change of heat with respect to temperature, keeping pressure is constant, we say it's specific heat at constant pressures. Now, with these two definitions, and we now recall the first law of thermodynamics, which is dq is equal to du plus pdv, and it is a non adiabatic process. So, when we have said this, then we start our definition saying that let us see that what is this internal energy U. We can write them as a independent function of temperature and volume. So, first we assume that U is a function of temperature and volume, then we can write what is du is equal to dou u by dou t at constant volume into dt, dou u by dou b at constant temperature into dv. Okay. So, then we can write this dou u by dou t and we can put it in this first law equations. So, from this we can find out dq by dt as a function of u du by dt at constant volume plus du by dv at constant temperature plus p into dv by dt. So, basically you divide by dt here, the dt will get cancelled and dv by dt will come here, and then you put that equation in the first law. Then when this equation is put in the here, we arrive at this particular equations. Here from this equation we now recall the parameter what is called as volume expansivity beta is equal to 1 by V dV by dt at constant pressure. Then we also have the Cv definitions, which is dq by dt at constant temperature, dq by dt at constant volume. When you impose this condition as constant volume, this parameter will go up. So, this first law expression becomes a which is nothing but the specific heat at constant volume. Then you impose the condition that when we write this particular first law equation at constant pressure. That means, when you say at the constant pressure conditions, if you impose that thing, then if you rewrite that equations, then we will find that this dq by dt at constant pressure is the Cp, this term becomes Cv and this term remains as it is, and this dV by dt we can get it from the volume expansivity, that is nothing but V times beta. So, finally, we have another expression du by dV at constant temperature is equal to Cp minus Cv divided by V into beta minus P. So, what I am trying to gain from this exercise, that we have this internal energy functions u, and this u, if you want to see this variation of u, means you want to measure du by dV at constant temperature, it is possible that through the information of Cp, Cv and beta, they are nothing but the property. So, through these things it is we are able to quantify this term. Another one is du by dt at constant volume, this is nothing but your Cv. So, what it says is that the internal energy functions, by definitions we can interpret it in the from the first law about the change of internal energy with respect to the independent property parameters, and in this case it is volume and temperatures. Then moving further to the heat capacity and measurements, we have another concept which in the basic thermodynamic courses we used to call as a heat reservoir. So, the word reservoir stands for the fact that as if whenever there is a change of temperatures, when you take out any heat from a reservoir, a heat reservoir, as if its temperature do not change. This something we can view, you can, if you want to take some bucket of water from a ocean or river, we do not view any change in the ocean systems as the change of mass. Similar way, for heat, concept of heat reservoir is utilized, where we can say that heat reservoir by definition is this infinite source of heat from which we can take out heat or we can add heat. This heat reservoir concept is very vital in understanding the subsequent law of thermodynamics, that is second law of thermodynamics. Now, from the first law principle we can find out that what is the, or we can find out what is the quantity of heat that gets transferred if by maintaining constant pressure, then we can write it as Qp as integral of Ti to Tf Cp dt. So, that we can say Cp times Tf minus Ti. At constant volume, Qb is equal to Cb times Tf minus Ti. So, this is the quantification of heat in terms of temperature difference. Now, after giving the very basic definition of work transfer, then we will see that what is the modes of heat transfer. So, we said that temperature difference is the essential requirement for transfer of energy in the form of heat, but we can say there are multiple phases of substance that occurs. Heat can be transferred in a conductor or in a solid body. Heat can also be transfer is possible in a liquid medium or in the gas medium. So, based on this medium, we define them in the form of heat transfer as its modes. So, the first mode is nothing but the heat conductions. So, it is referred as a conduction mode of heat transfer when the transport of energy is possible from one volume element to a neighboring volume element through this temperature difference. So, it is a heat conduction. So, it is a volume is taken as one parameters. The Fourier's law of heat conductions is introduced that talks about this heat conduction mode. So, it is represented by equations dq by dt is equal to Ka dt dA dt by dx, where it introduces a term which is called as thermal conductivity, and this thermal conductivity and also the change of heat with rate of change of heat is proportional to the area, surface area and the temperature gradient. So, there is a term which is negative sign introduced because the dt by dx is always a negative quantity, because it flows from higher temperature to the lower temperature. Now, to make this entire quantity positive, a negative sign is introduced. Now, from these basic definitions, we can find out what is the thermal conductivity of a particular material, and its SI unit is represented as watt per meter into Kelvin. Now, moving further, when the medium is liquid, we call this as a mode of heat transfer as convection, or it can also be a gaseous medium. So, the convection means that by virtue of temperature difference, a convection current is introduced. That means, for example, when you boil water, what happens? We are giving heat at the bottom surface of the container. So, temperature drops. When the temperature increases, but density drops. So, by virtue of which the higher density mass will come down and the lower density mass will go up. Through this process, the communication of heat happens, and as long as this goes and as long as we are supplying heat, we say that this particular motion we call this as a convection current. And if this convection current is possible naturally, that means without involving any external agency, or it can only occur through this temperature difference, then it is a natural convection. So, if the convection current is produced by an external agency like running a fan or pump, then we call this as a forced convection. So, in a heat convection there are two parts, natural convection and forced convections, and for all this case the parameter which is of importance is the convection coefficient H. So, dq by dt is represented as is equal to H into A into delta T, where H is the convection heat transfer coefficient, A is the surface area and delta T is the temperature difference. So, the convection coefficient depends on many factors like nature and geometric configuration of the wall, nature of the fluid, property of the fluid, specific heat, nature of the flow, whether it is laminar or turbulent, also the thermodynamic process, evaporation, condensation or scale formations. The last part of heat transfer study, we call this as a heat radiations. heat radiations also occurs for as a temperature difference, but this there is no thermometry concept is introduced. So, it is means when the temperature it does not fall in the range of gas thermometry. So, in this case and in this case it is viewed by the radiation waves, and typically we call them as electromagnetic waves. These electromagnetic waves falls as a radio waves, microwave, infrared, visible range or ultraviolet range, X-ray and gamma ray, and they differ in frequency and wavelength. Then while talking about the radiation, we characterize this radiation as radiant power. So, this radiant power is termed with respect to radiation existence, which means that it is the radiation power that exists from an infinitesimally small surface when it is divided by its area is termed as radiation existence, and it is or simply R, and this value of R changes with temperature. For example, for a material like tungsten, the R value is 6.5 kilowatt per meter square when its temperature is 1000 degree Kelvin, but when the temperature increases its value changes. Temperature increases to 2000, this number R value can be of 1535 kilowatt per meter square. So, it means that radiation existence is a function of temperature and of course, with the material. Another important factor in the radiation is the emissivity, and this emissivity term is defined as the fraction of radiant power for a real body which is emitted from the surface with respect to total power, and it is referred as the black body radiations. And this black body radiations depends both temperature and the nature of emitting surface. So, once you have, there is another term which is called as irradiance. So, it refers to because when you say view this radiation, we can say there is a cavity, as if there is a cavity, a small cavity which radiates, and that means which have enough radiant power and radiation is comes out of it, and that term is called irradiance. When the radiate existence of a black body occurs at the same temperature. For example, there are two bodies, one is black body which has certain temperature T, we found its radiant power. There is another body which is not a black body, and if you want to calculate its radiant power at same temperatures, then that term we will call as irradiance. To quantify this, the first concept that was introduced is Kirchhoff's law, which says that radiant power or radiant mode of heat transfer dq by dt is equal to A epsilon times T, radiant power of black body at temperature Tw, and radiant power of black body at any temperatures. So, this particular expressions was bit complicated, and further it was simplified by using Stephan-Boltzmann's law, where this radiant power was quantified as proportional to the temperature to fourth power of the temperatures. So, we can rewrite this Kirchhoff's law as Stephan-Boltzmann's law, and which is most widely used as of now, which says that dq by T dt is equal to A times epsilon sigma into Tw to the power 4 minus T to the power 4, where epsilon is emissivity, R is the radiant existence, A stands for the area of non-black body, and here it is introduced a term which is called as Stephan-Boltzmann constant. So, with this I have come to the end of this particular lecture, where we have introduced the important concept work, heat, internal energy and subsequently formulation of first law. So, the first law gives the indication of internal energy, enthalpy and the quantification of internal energy as a function, the functional form of internal energy can be evaluated from the first law mathematically. So, now we will try to solve some very basic problems as far as the work transfer and heat transfer is concerned. So, the first problem concerns about a kind of a situations when there is a change in the velocity, and the change in the velocity is associated with the change in the kinetic energy, and that how that kinetic energy can be related to work transfer thermodynamically. So, the first problem says that we have to calculate the power required to accelerate a 900 kg car to a speed of 80 km per second in 20 seconds. So, it is initially we can imagine that the car is at rest. So, V 1 is equal to 0 and V 2 is 80 km per hour, and this can be changed to meter per second, that is 80 into 5 by 18 meter per second. So, this turns out to be 22.2 meter per second. And the rate of change of kinetic energy, we say it is power, this W A we can write half m V 2 square minus V 1 square, and V 1 is 0 here. So, this turns out to be half into 900 into V 2 square is 22.2 into 22.2. So, this turns out to be 222 kilojoule, and this much power we have to, this much work we have to use in 20 seconds. So, power requirement P A would be W A by T time. So, 222 by 20, so it is 111 kilojoule per second or kilowatt. There is something wrong. So, this number would be, so this number would be 11.1, 1 kilojoule per second. So, it will be 22.2. So, P A would be 11.1 kilowatt. And in the second problem, the car is going to climb. This climb means with an, and this angle is taken as 25 degree. So, your movement is in these directions. So, vertical is V vertical speed of these things, and we have horizontal speed. So, we can rewrite this equation that when the car is climbing in a slope road at an angle 25 degree with same condition as the question 1, and the velocity of the car is to remain constant, then we can put the power requirement as W B, and that is nothing but m g times v vertical velocity of the car, that is m g vertical velocity will be v sin 25 degree. So, W B one can quantify, mass is 900, g is 9.81, velocity is 22.2, because we are not going to change the velocity, and sin 25 degree. So, this term would be, 76.36 kilowatt. Okay. So, the next problem is about the heat transfer. So, we are looking at a person who stands in a breezy room, means it is a, there is a breeze of wind and this wind room is maintained at 20 degrees centigrades. We have to calculate the heat transfer if the exposed surface area and surface of the outer area temperature is 30 degrees centigrades. Now, here the first thing that you need to understand is that what are the possible mode of heat transfer from the person. So, the possible mode of heat transfer we can write Q as Q convection is possible plus Q radiation is possible. Now, Q convection requires H A delta T and delta T is known here 30 minus 20 10 degrees centigrades. Area is 1.6 meter square and here we have to assume for convection heat transfer coefficient. So, this typical number can be 6 watt per meter square for this kind of situations. So, this number I have assumed maybe for a normal temperature breezy wind natural convection value the H can be of this number. So, Q convection can write 6 into area is 1.6, delta T is 10. So, Q would be 96 watt, that is convection. Other part of radiation you can quantify as sigma epsilon A T 1 to the power 4 minus T to the power 4. So, if I say T 1 as 30 degrees centigrades, so it will be 303 Kelvin, T 2 20 degrees centigrades, which is 293 Kelvin. Sigma value can be assumed as 5.67 into 10 to the power minus 8 watt per meter square into Kelvin to the power 4. Epsilon for a room a realistic number could be 0.95. That means, for a human body the emissivity term is of this number. Area is again 1.6 meter square. So, by putting this we can quantify radiation heat transfer as 66 watt. So, you can say that total heat is 96 plus 66 162 watt. And of course, this number is very small, which we normally do not realize, but still the convection and radiation heat transfer at room temperature is possible. So, with this I conclude this presentation today. Thank you for your attention.